Okay guys, so what I want to show you today is something that I mentioned briefly in before you wrote your exam, is the power of that one formula, and that formula literally can answer almost any physics question, mechanics question, and what it boils down to is it comes from this formula that the net work done is equal to the change in kinetic energy. And this is true no matter what the circumstances are. Okay, it doesn't matter if there's friction or if there's gravity, it doesn't matter if it's kinetic. Well, it's not used for collisions. Okay, this does not involve collisions. This assumes, the only thing it assumes is that if there's acceleration, it's constant acceleration. Okay, so for example, in a collision, all of a sudden acceleration changed. There's an object maybe going at a constant velocity and then colliding with something else that causes its acceleration to change. There's a change in acceleration. Does that make sense? Or I might be speeding up and then hitting something. So for example, if I drop a ball, then for the time it falls until it hits the ground, this will apply. The moment it hits the ground, there's another acceleration at work. And then I will split it into two sets. I will now, in the one set, I'll work with this formula. And then if I want to consider it going up again, I can use this formula again, but in a separate scenario. Does that make sense? Okay, we'll look at a few examples, then maybe it will make sense. Okay, so can you guys see there? Is that fine? Can all of you see?
Yes.
Okay, cool. So just so that you understand why I say this can answer almost everything, what you need to understand is what we mean by net work done. Where do you use, or where have you heard the word net often? Where do we often use net? Not necessarily in maths or science.
Accounting.
Sorry?
Accounting.
Good. How do we use it in accounting?
Net profit and loss.
Okay, so it's net. Do you call it net profit?
Yeah, we do.
Is it? Okay. So, what is net profit?
I remember.
You don't remember? Who knows? What is net, or net income? Let's say that. Net. What does net mean?
Isn't that where all your expenses mean?
Like when you add all the forces, that's what you said. When you add all the forces in an object.
Okay.
Yes.
Yeah, it's literally what it is. But the point with your net force is when you add all the forces, but you keep in mind that we're adding vectors. And some vectors that's in the opposite direction should then have a negative sign. So it's not literally just adding all of it. It is adding all of it, but some of them you add a negative number, so you're actually subtracting it. Okay, so it's adding and subtracting. You add your, so let's use it like that. Don't write this in the exam. Okay, net means it's income minus expense. It's what you get in and what you expend. So your net income is all of your income minus all of your expenses. Okay, so we have our work income and work expenses. Okay, now I'm just saying it like this so that you can understand what I mean. Change in kinetic energy. So what I mean is that work done is literally energy that's being put into a system, or energy that's being taken out of a system. Okay, so if I am pushing, or if I have an object, for example, on an incline, oh, it's a weird looking object. Okay, but if I have an object on an incline, depending on the direction in which the object is moving, that will determine what will be the income. Okay, all of the energy that goes in the same direction would be energy that comes in. All of the energy that goes in the opposite direction would be energy that I must subtract, work that I must subtract. So for example, let's say it's being pushed up the system. up this incline. So if it's being pushed up the incline, there is work being applied. Does that make sense? Applied work is always when either there's an engine involved or someone is pushing it, or applied work is something that doesn't just exist naturally. It has to be applied. It's work that's done by something, okay, or someone, or either a machine or a person, okay? So that's the one force acting on this thing, or the one place where we can get energy from. The other work being done is the work done by gravity. The work done by gravity is down, okay? Would that be in or against the direction? So let's circle things with green if they're income, and with red if they're expense. That would be income, because I'm pushing it in the direction of motion. Well, hopefully. Okay, hopefully this thing is not rolling down. It could be. I could be stopping something or letting something go downhill at a, so for example, when your car goes downhill, you don't just let go of everything, okay? You actually apply the brakes, which means you're applying work, but in the opposite direction than it is moving. Does that make sense? Okay, so that's a good example actually, but in this case, let's say we're pushing it up the hill and it's moving up the hill. So let's do the direction in blue. It's going in that direction. So work applied would be an income. Gravity, what do you guys think? Gravity be an income or an expense in this system?
Expense.
It would be an, can you understand why it's an expense?
No.
So, if I'm pushing something up an incline, can you understand that gravity is stealing from the energy that I'm putting in?
No.
Does that make sense? It's subtracting from the part of the applied energy that I'm putting in must overcome gravity because I'm trying to push it up an incline. So there's work being done by gravity, and that one's going to be an expense. Make sense? What else can do work in our system? What else can contribute energy or steal energy?
Friction.
Friction.
Yes.
Friction will always be an expense. So friction is always in the opposite direction as motion, and if there is friction involved, it will always be an expense. Okay, so here we go. This is, if this was my scenario, this formula here will change to the following. I will take all my incomes. Where's my incomes? I only have work applied as an income. Now I'll have to subtract all my expenses. I am subtracting friction, and I'm subtracting energy done by gravity. Now, if this is a positive answer, it means I am applying more energy than is being taken. Does that make sense? So what is happening with the energy that I'm applying? I'm giving it more. Okay, let's say this. If this was zero, if my net work, if my net energy is zero, what would happen to this object?
It's gonna stay stationary.
Jessica says it will stand still. Do you agree with that? Look at this. The net work done is equal to the change in kinetic energy. What is kinetic energy? Let's try and understand. What is kinetic energy?
The work applied to a force.
No, what is kinetic energy? If I say I have kinetic energy, do I have kinetic energy now? No. Do I have potential energy now?
Yes.
Yes, because I can fall off the chair. Okay, I am above the ground. I don't have kinetic energy because I'm not moving. Okay? So kinetic energy is the energy that I possess because I am moving. kinetic energy's formula is a half mass times my velocity squared. So the heavier I am, the more kinetic energy I will have. Like if I'm running at 5 meters per second and an elephant is running at 5 meters per second, the amount of energy that that elephant has is more than what I would have. Okay. Make sense? The amount of kinetic energy there. Are you sure it makes sense?
Is it the elephant? Is it something about the elephant?
Yes, I said he would have more kinetic, even though we're going at the same velocity, the amount of energy that he has is more than the amount of energy that I have, because kinetic energy is a product of mass and velocity. If I wanted to have the same kinetic energy than he has, I would have to travel at a bigger velocity because my mass is much less. Does that make sense?
Yes.
Okay, so think of energy as something that can be converted into something else. So for example, electricity can be produced from something that rotates. Okay, you guys have done matrics. I know you know, what is that again? Which motors are those? Doesn't matter. It can be produced. So in other words, a person running on a treadmill can produce electricity because they have kinetic energy is being changed into electric energy. Does that make sense? Okay, cool. So, Jessica, are you sticking to your answer?
Yes.
If net work is 0, then an object will be stationary. Okay. If kinetic energy, so are you saying it will be stationary because its kinetic energy will be 0? If something is stationary, its kinetic energy is 0. Isn't that's true? Isn't it? So you are correct that if it is stationary, then its net work done must be 0. Because if I am stationary, my kinetic energy is 0, and so the net work done on me is nothing, because the forces, the energy that's put in and the energy that's taken out is the same. But it doesn't mean that if network, so listen carefully, if my kinetic energy is 0 for an extended period of time, if I'm stationary, doesn't mean I've stopped. It means I've stopped and I keep on stopping. Does that make sense? For example, if I throw a ball up in the air, when it reaches its highest point, is it stationary?
No.
No. Is its kinetic energy 0?
Yes.
Yes. But not only for that moment. It's 0. So okay. So what I'm saying is, if my kinetic energy is 0 and it stays 0, then I'm stationary. Does that make sense? I'm not stationary just because my velocity is 0. It could be 0 just for a second, or not even a second, just for a moment. Okay, so understand that. What I'm trying to show you guys is that net work done is equal to the change in kinetic energy. So if I'm stationary, it means my velocity is not changing. Now, if I'm traveling at a constant velocity, it's the same thing. My velocity is not changing. Just because my net work done is 0 doesn't mean my kinetic energy is 0. It means my kinetic energy is not changing. Does that make sense? Now, what does it mean if my kinetic energy is not changing? About my motion. What does it mean about my motion? I could be stationary, yes. My velocity could be 0 and stay 0. What else could it mean?
Can it mean it's constant?
What is constant?
Moving at a certain speed.
Your velocity is constant. Yes. So what do we call it if my velocity is constant? What does it tell me about my acceleration?
0.
Yes, there's no acceleration. So if my kinetic energy, if my inputs and my outputs are the same, then it means I am traveling at a constant velocity. Where am I going to put that? If 0, then the change in kinetic energy is equal to 0. If change in kinetic energy is equal to 0, it means that half my mass times my... Okay, now, this is something that people do wrong. They say change in velocity squared. That's not the formula, okay? Change in kinetic energy is the change in the squares. In other words, it's future velocity squared minus initial velocity squared. Okay, so if my future velocity and my initial velocity is the same, then it means there's no change in my kinetic energy. Does that make sense? Because then future velocity minus initial velocity will give me 0, and half times my mass times 0 is equal to 0. Okay, so that's if it is the same. What I'm trying to tell you is that if my net work done is greater than 0, come interpret that for me a little bit now. What does it mean if my net work done is greater than 0? Don't look at this relationship. Tell me, what do I mean if I say my net work is greater than 0?
I mean it's positive.
It's positive, that's good. What does it mean if I say my net work is positive?
I think it's an income.
Very good. Okay. It means I am putting more energy in than is being used up. So now the question is, what happens to that energy that I'm putting in?
Makes the object move.
It makes the object, it's already moving,
Well,
move
continue
faster.
move faster.
It makes it move faster. It increases the velocity. So in other words, now I'm putting energy in, but I'm putting more in than it needs. If I'm putting the same in than it needs, I'm just keeping it moving at that constant velocity. In other words, I'm overcoming gravity and I'm overcoming friction. So the energy I'm putting in, if I didn't put that energy in, then gravity and friction will win. They will slow the object down. But if I put more energy in than the gravity and the friction is taking away, it means I'm giving the object more energy. How do I give an object more energy? I'm making it move faster. It's already got energy because it's moving. Now I'm giving it energy either by overcoming friction and gravity, or I'm giving it enough energy to make it move faster, thereby giving it more energy. Petra, you look confused.
I think I get you.
You think you get me?
Yeah.
Okay. Are you sure?
Yeah.
You get it? It's really that simple, and you'll... okay, so if my net work done is greater than 0, it means my change in kinetic energy is greater than 0, which means it is... Again, remember, I'm not talking about kinetic energy. Kinetic energy is bigger than 0 because the object is moving. Okay, the change in kinetic energy means, so let me write that down. That means if I take my future kinetic energy minus my initial kinetic energy, that must be greater than 0. That's what the change in kinetic energy is. Hudson, this yellow is boring me. Okay, so just think of maths now. I've got a quadratic equation here. Not a quadratic equation, inequality, and so I'm just adding this term on both sides. So I've got greater than a half mass velocity square. Notice there, this is my future kinetic energy is more than my initial kinetic energy. Does that make sense? So when I'm applying this force, I'm causing my future kinetic energy to become greater than my kinetic. Now if it's less, if my net work done is less than 0, it means the amount of energy that I'm giving is not enough to overcome the energy that's used by gravity and by friction. Which means, where is gravity and friction going to get the energy that they need from?
Object.
From the object, because I'm not giving it. Does that make sense? So what energy does the object have? It's got energy because it's moving. And so it starts stealing that energy from that object, so that my future, in the same thing, just the sign is reversed, my future kinetic energy will now be less than my initial kinetic energy. Does that make sense?
So the object will move slower.
It will start slowing down. Yeah, it will move slower and slower and slower and slower until it stops. Because then it doesn't have any energy to take from anymore. Okay. Obviously, this object is now going up. Okay. So its kinetic energy will be, if I take upwards as positive, its kinetic energy will be positive. And if friction and gravity starts overcoming, stealing all of the kinetic energy, at some point kinetic energy will be zero, and then all of a sudden kinetic energy will become negative because gravity is still pulling on it. So now, so let's look at that. Let's now assume that we have an object on an incline. Let's take this object. It's not going to look nice. No, it's not going to work. Stick to the circle. Okay, so there's my object on an incline. Okay, so now let's look at it going down. Going down. Now, it doesn't matter where you are applying the force, as long as you remember that if you're applying it in the same direction, you're an income. If it's in the opposite direction, you're an expense. So if we say my net work done is equal to my change in kinetic energy, my net work now, I must consider all the incomes. Let's look at all the forces applied. So let's assume I'm pushing it down the hill. Okay, or actually let's assume I am slamming on brakes. So I'm applying a force in the opposite direction. Okay, so let's say that's the case. So the energy that I'm applying is in the opposite direction as motion. Gravity is always downwards. In this case, will gravity be an income or an expense?
Yeah.
An income. It is working for the direction. It is helping it go down the hill. It is the reason why it is rolling down the hill. Okay, and friction, in what direction will friction be? Will it be an income or an expense? Always an expense. Friction is always an expense. So like my net work done will now be, okay, all my incomes, which is the work done, which energy gives me income? Gravity. Gravity is the only one that gives us income. So gravity is an income, and these two are all expenses. So I will subtract the work applied, I'll subtract the work done by gravity, and I'll have change in kinetic energy. Okay, do you see? That would be your first step to answer a question. So they give you some sort of question, and if you want to, if you can see, okay, I can use this formula, and you can quickly try it, see if it's going to work. Then once you know what your formula is going to be, see, it's not a fixed formula. Okay, so as you can see, it's not a fixed formula. It's not like you can always use this formula, always that formula, but it's a fixed idea. You can always say, what is the energy that goes in and what is the energy that goes out? Whatever is extra changes the kinetic energy. Now, let me just show you how powerful this formula is. Let's take this one, for example. The work done by gravity minus, so all you need to know is this is called the work energy principle. Okay, that always applies, assuming that I'm just considering one acceleration. So remember, my kinetic energy is now changing. but I'm just assuming it's changing once. So for example, my kinetic energy of a ball dropping. Okay, during the time it's falling, it's got the same constant acceleration. The moment it hits the floor, that acceleration doesn't apply anymore, because now there's another force again acting in the opposite. There's energy coming from another place now. And so I can still use the formula, but I must use them in two different parts. I'll use the first formula maybe to get the velocity, the kinetic energy it has at the bottom. Then I'll start my story afresh and say, okay, well, this is now the scenario. This is now where we get energy from, etc., etc. Okay, so let's use this one, for example. Work done by friction is equal to the change in kinetic energy. So I just want to show you, that's the one thing you need to know is this. You need to know the principle of income and expense, and the next thing you need to know is the formula for work and the formula for kinetic energy. Let me show you. So the formula for work is equal to force times change in displacement, and the force, that's a capital F, sorry, force and the displacement must be in the same direction. Okay, I'll explain that just now. If in this case you'll notice that gravity is not in the same direction, it's not in line is what I mean. It's not in line with the motion of the object. Okay, so what I'll need to do is I'll need to use the displacement that is downwards. Okay, in other words, I'm not going to look at this distance, I'm going to look at that distance. Does that make sense?
So, but why that distance? Why not that one?
Because the work done, work is only done in the direction of the force. So that's how work is defined. Work is defined as the force applied in the direction of x. Now this thing's direction, the change in its displacement, yes, it's got a displacement here, but I can break that displacement up into displacement over height and a displacement over length, however you want to call it. Okay, now if I talk about work, since gravity is downwards, I need to consider what was its change downwards. So for example, the work done by gravity is equal to what do we call the force of gravity? What do we call the force of gravity? Gravity is the acceleration really that it experiences. But what do we call that force?
Acceleration due to gravity or something.
Yeah, it's called weight.
Oh, weight. Yes.
Weight is the force of gravity. Does that make sense?
Yes.
Okay. How do we calculate weight?
Mass times gravity.
Mass times gravity.
Yes.
So the work done by gravity is the force of gravity, which is mass times gravitational constant, 9.8, times, and now this is going to be the change in the height. Mass times gravity times change in height is what? So in other words, work done by gravity now has the formula mass times gravity times the change in height. Now, the work done by the applied force is equal to the force applied. It's the same formula. We just need to consider what is the force that we're talking about. It's the force applied. I'm putting on brakes, so I'm applying a force times, and the force applied is in line. It's not in the same direction, but it's in line with my motion. It's in the same line. That's important. Does that make sense? Okay. So force applied is in the same direction as my displacement. Now technically, the real formula for work is force times displacement times cos of theta, where theta is the angle between the force and the displacement. Okay, but this part just calculates the component of the displacement that's in the direction of the force. Okay, so for example, H, delta H is, if that angle here is theta, then delta H is delta X times cos of theta. Okay, so in the case of work applied is force applied times delta X times cos of theta. Now if the force applied is in the opposite direction, then the angle between force applied and X is 180, so force applied is delta X times cos of 180. That is if it's in the opposite direction, but cos of 180 is -1, so this becomes negative force applied delta X. But we've already considered this negative. I've already considered cos of 180 by considering what is an expense. By thinking of it as an expense, I've already done the cos theta part, so I can leave it out. Unless, of course, the force is applied at an angle. Then I'll still have to add that angle. But as long as it's not an angle, as long as it's in the straight line, I'll keep it like that. The work done by friction, exactly the same. It's my frictional force. Okay, and this, important for us, is it is kinetic friction. Kinetic friction means it's moving, times delta X, and again it should be cos of 180, but then it should have been plus. But since cos of 180, because the force of friction is in the opposite direction, it will always be cos of 180, and therefore it will make it negative. Now I've already considered that 180 by considering friction as an expense. Does that make sense? That's why I don't need to put in my cos of 180. Is equal to my change in kinetic energy. Change in kinetic energy is a half mass times future velocity minus a half mass times initial velocity. Now I just want to show you the reason why I wrote this out. Every single, every single parameter that you can calculate is in here. We've got frictional force is in there. We've got displacement is in there. We've got future velocity, initial velocity, force applied. We've got change in height. We've got mass is in there. You see every possible value. Is there a value that you can think of that they might ask you?
The normal force. Or they don't ask for the normal.
The normal force doesn't do any work, but it's a good question. What is the force applied by the normal force? But the normal force has its unique formula where the normal force is equal, I never remember the formula, negative weight times cos of theta. Okay, so the normal force, but you can work out the normal force by just going to look at weight is down, normal force is perpendicular, perpendicular, weight is down, it will be longer than the normal force, and then all you need to do is recognizing that if I move this weight here, now put this there, and this is theta, and since you are That's theta. Okay, so this is theta. That angle there is theta. When I put the normal force and I put this weight head to toe with my normal force, then that is theta. Now I'm given the weight. Here's the weight. I want the normal force. And now if I could, let's see if I can turn this around. Don't know if this program can turn it around. I don't think so. Anyway, if you now look at this, this is now actually a triangle that looks like that. Let me just put it down on its side, like that. Can you see me how I've put it on its side? So this is now the normal force. That's the weight. There's a 90-degree triangle. I've just put this side down here. You see that? And then this is theta. So I have my adjacent and my hypotenuse, which is cos. So cos of theta is my weight divided by my normal force. So all I do is I multiply to get my normal force. Normal force is equal to weight divided by cos theta. Okay, sorry, so I got my formula wrong there. Is that true? Did I do it correct? No, those two are wrong way around.
Yeah, it's normal force over weight.
Yes, sorry. There's normal force over weight, thank you. Yeah, see your trick is paying off. Sorry, it's adjacent over hypotenuse. So it's adjacent normal force over weight. Okay, I thought so. Okay, so my normal force is just weight times cos theta. The reason why I put the negative in is because the normal force is in the opposite direction than weight. Weight is downwards, normal force is upwards. So I put the negative in there to indicate direction. Okay, so that's a fixed formula. When you work out normal force, it's not a normal force cannot do work. It cannot be used in this formula. Sorry, it's a good point. Because it's 90 degrees, yeah?
Kinetic friction, does the displacement, is it the same with the one of the applied force?
Yes.
We use the same one?
The same one, yeah. Unless your applied force is not, so for example, if I'm pulling on this chair, I can pull on it like this, or I can pull on it like that. Now when I'm pulling on it like that, I'm making an angle. And if I increase that angle, instead of pulling it, I will be lifting it up. Do you see? So in other words, when I pull at an angle, some of the energy that I'm putting in is lifting it up. So for example, when we pull on something heavy, we lift it up a little bit, isn't it? And then we pull on it so that less of it touches the ground. So some of my energy goes into lifting it up, some of it goes into pulling it. But when I'm pulling it straight, all of my energy goes into pulling it straight. Does that make sense? So that's why when I'm saying friction force applied, I only consider the force that's applied in the direction there. So if it's not, then I have to change my force applied to be force applied times the delta x times cos of theta. If theta is now the angle between the angle that I'm making with its motion. Okay, so it's very seldom that it applies, but there is an example that we're going to look at where it does come into play. Okay, I know we've just been doing all of this, but can you think of something else? There's one value not in there. Yet.
Tension.
Tension is force, net force minus mass times acceleration. We'll maybe look at that, mass times acceleration, yeah. No, that's 0 mass times gravity. We'll look at that. Okay. Let's go look at a few examples, I think, and then we'll see how it applies. Okay, so here we have question 2 in our mid-year exam. I'm not going to go through all of the, especially the theoretical questions. You're supposed to know that. Flynn Rider is let down with a single rope into a palace room where the princess's crown is guarded. 2 bandits on the top of the roof apply a constant force to the rope, which makes an angle of 45 degrees with the roof, in order to slow the descent of Flynn as he's lowered 5 meters into the room. Okay, so he's lowered into the room 5 meters, and so I don't have the picture there, but basically it looks like this. 2 bandits are pulling on here. The angle is made 45 degrees with the roof. Okay, there is Flynn hanging, and they're letting him down, and then the distance here is 5 meters. Okay. Flynn then steals the crown and is pulled up by the bandits in order to make an escape. Now, the first question, construct a force diagram with all the forces acting in on Flynn as he is suspended in a stationary position above the crown by a rope tied to his body before stealing the crown. So if we do our force diagram, here's Flynn. What are the forces acting in on Flynn as he's hanging there?
Gravity.
Gravity is always a nice one. Gravity is not a force, guys. What is it? Weight. Okay, so this gravitational force is weight. Okay, now, is that the only force acting in on him? If it was, he should be falling. That's what we define as free falling. And why are you falling? Because there's only an income of weight, and so there must be an opposite one. What would this be? Normal force only applies when I am on a surface. I'm not on a surface. Normal force is the force that a surface applies to me that causes me not to fall. Make sense?
Yes.
So what?
Applied force.
Applied force. The bandits are, there's an external force. It's not friction, and it's not gravity, and it's not normal force. The only one remaining is applied force. So that's force applied. Flynn has a mass of 60 kilograms. That's the only forces acting in on him. People drew funny things like that. I have no idea.
That was one of them.
Yeah.
Is it? Yes, you had normal forces in there, so apparently. I did actually. So don't go through everything now. We'll go through as much of the mechanics as we can. Now they say Flynn has a mass of 60 kilograms. Calculate the horizontal component of the force that must be applied by the 2 bandits on the roof to have him pulled up to the top of the roof within 10 seconds in order to escape in time. If there is a frictional force, and there's the friction, between the rope and the surface, okay, so they give us the frictional force, the rope still makes an angle of 45 degrees with the roof. Okay, so let's just go and take, and you'll see there we also don't have time in this one. We also don't have time here in this, and yet they give us time. Now, time might not be in here, but I want to show you something else here. In this part of the formula, if I take out a half mass as a common factor, a half mass, then I'm left with future velocity squared minus initial velocity squared. Okay? future velocity squared. If you remember, there's one formula that says future velocity is equal to initial velocity squared is it plus 2 a delta x, isn't it? Okay, so future velocity squared minus initial velocity squared is equal to 2a delta x. Okay, so in other words, this formula can also be a half mass times 2a delta x. And it can also then, if I multiply it out, it can be mass times acceleration, because 2 times a half is 1. Mass times acceleration times delta x. Mass times acceleration is net force, delta x. I don't want to go too much into it. We'll see change in kinetic energy can then also be written as, or net work. Net work done is the net force times delta x. That's how we define work. But net force has another definition, income minus expenses. Okay, and net work done is mass times acceleration times delta x. So there's one value that's not in here, and that's, or two values, that's acceleration and time. Okay, but what formula has time in? Future velocity is equal to a future velocity, acceleration is future velocity minus initial velocity over time. And so in this formula, so in other words, if I have my net work done, I've got my whole formula with net work in it, and I have that's equal to mass times acceleration times delta x, I could just replace acceleration with mass times future velocity minus initial velocity over time times delta x. Do you get what I'm saying?
No, not really.
Okay.
No, when this part, I lost you when you were talking about this part. This part.
So I just took out a half mass as a common factor, and then I'm left with future velocity minus initial velocity squared. But future velocity minus initial velocity, if we use this formula, we notice future velocity minus initial velocity squared is equal to 2 delta. So I just replaced that part with 2a delta x.
So what happened to...
And now if I multiply in, there's still a half there.
Oh, okay.
And now the 2 multiplies the half, and that becomes 1. And so I just have mass times 11, which is net force, which is, again, it's actually where this formula comes from. Okay. So, okay, but I won't say too much. I'll just, well, I've said too much already. Okay. So let's quickly go and see. So here he's hanging, and they want to pull him up within 5-10 seconds. They want to pull him up. What is going to be incomes and what is going to be expenses? Give me an income.
It's going to be an expense.
Sorry?
Weight will be an expense.
Weight will be an expense. Let's start with the incomes though. Applied work. So they will apply some work. Okay. This, by the way, is not supposed to be done with this formula. It's supposed to be done in a different way, but you can use the formula. So work applied. It's income. What else? Is there another income? Anything that will work in his favor going up?
Yes.
What? No. The only reason he's going up is because people are pulling him up. Okay. If they let go, then everything will let him fall. So in other words, the rest, the work done by gravity and the work done by friction is working against them. And this must equal his change in his kinetic energy. Okay, now let's go and put work applied. And so what are we supposed to calculate? They say we should calculate this component of the force. That component of the force. Okay? In other words, we should calculate this. This is the force applied. Would you agree with me? That's the force applied. And that force applied and the upward force applied is exactly the same. The rope is just bent at the side of the roof. Okay? So this question I think counted something like 9, 7 or no. Can't remember now. So 7 marks. Only 1 mark went for getting the horizontal component. Most marks go into calculating what was the force that they applied. And then we just get the horizontal component of that force. So let's just focus on getting the force applied. Let's forget about cos of theta. We'll get 90% of the marks just by calculating force applied. Okay, so let's see what is the force that they applied. In other words, what is this value? That's all we want to know. What is that force applied? Okay, so force applied delta x, that is for work applied, my income, minus my expense. Work done by gravity is weight, which is mass times gravity, times his change in his height. What would be the change in his height? 5 meters, because he's hanging 5 meters below the roof. Can you remember here they say again? They say that, so if I'm pulling someone up, obviously the change in my height is how far am I pulling them up. And here they say, where is it? He is lowered 5 meters into the room. Okay, so I have my height. My change in height is going to be 5 meters. Minus the work done by friction is simply my kinetic friction times the change in displacement. Now my change in displacement and my change in height is the same thing because I'm only moving horizontally up and down, vertically up and down. Okay, is equal to my change in kinetic energy is half times my mass, and then I've got future kinetic energy minus initial kinetic energy. Like that. So let's put everything in that I have. If there's something I don't have, I'll see if there's not a way I can get it. Okay, let's see. Do I have force applied? No, that's what I'm trying to calculate. Do I have the change in displacement? How far he's moving?
Yes.
How much is that? 5. Do I have his mass? 60. I know gravitational constant is 9.8. Do I have the change in height?
Yes.
5. Do I have the frictional force? Yes, 12. Do I have the change in height? Change in delta x? Yes, that's 5. Do I have a half mass? Do I have mass is 60. Do I have his future velocity? The velocity he's going at the time that he reaches the top. We don't have that. That's one problem. We don't have future velocity. Can you understand why not? Do we have his initial velocity? What is his initial velocity? His initial velocity is 0 because he was hanging stationary. Now they start pulling him up. They pull him up in 10 seconds time. They want to pull him up. And the question is, how much force must they apply? Now, I just want to show you guys how many marks you get just by, first you get a mark just for that formula. Next, you get a mark for each one of these. Just there, you got 5 out of, okay, you don't really get that mark because you would get the mark for future velocity there. But I mean, that's already 4 out of 7 marks. You're already passing this question, okay, just by substituting in there. So let's just see, how can we get the future velocity? How can we get future velocity? What do we call those formulas that we're going to use? The motion equations. Okay. which one has enough, what motion equation has enough information of, or what do we have? We have initial velocity, VI is 0. What else do we have? Time, we have time is, was it 10 seconds? 10 seconds. Okay, what else do we have?
Displacement.
Displacement. And we only need 3. So we will use my future velocity. There's the formula that says my displacement is my average velocity, future velocity minus initial velocity, plus initial velocity divided by 2. That's my average velocity times time. So 5 is equal to future velocity plus initial velocity, which is 0, divided by 2 times 10. So future velocity is equal to 1. That makes sense? Because 1 divided by 2, I just solved it, I just did it quicker than. So I multiply the 2 on both sides, and then I get 10 is equal to 10 times future velocity. So future velocity has to be 1. Okay, so 1 meters per second. And so we can go substitute. Let's go substitute our 1 meters per second. So a half times 60 times 1 squared minus 0 squared. And now it's simply solving the force applied. So I've got 60 times, so this side would be 30. Here I've got 60 times 9.8 times 5 is minus 2980, was it? 940, 2940 minus 12 times 5 is 60. So now force applied, 5 forces applied is equal to, when these go to the other side, so this becomes 3000, these two, 3030, 3030, so force applied is equal to 3030 divided by 5, it's the same as multiply by 6. Okay. And there, that would have given you already, out of the 7 marks, 6 out of the 7 marks. Because we get another mark here, which is the 5th mark, another mark for your force applied, and now we just need to know that's the force that is applied on this rope. But they want the horizontal component of the force. They want the force in the direction of x, not x really, but in the horizontal direction. So in other words, we're just trying to find out what is, this is a triangle, what is the adjacent. So in other words, the horizontal component of the force, we usually write it like this: force applied in the direction of x, so we're talking about the x-axis, is equal to, and you can again see we're trying to work out the adjacent side, having the hypotenuse. So that is again force applied times cos of theta, which is 606 cos of 45 degrees, which is 45 cos times 606 is 428.51. Okay, and since we have to put direction horizontally, that's the only thing we know about the direction of the force. This one, if we add a direction here, it should have been upwards. So upwards, it's applying 606 newtons. Horizontally, that would equate to 428.51. Okay. How's that? Do you see? What do you think about this formula? You see, this is a very difficult question, by the way. It's a very difficult question. But I think with the formula, it's not really. The only challenge was really getting future velocity. It's really the only...
So all you have to do is kind of like play with them.
It's exactly what you're doing. Is you're trying to play with this formula, use values, try and find a type of formula that will work. I can show you how to do this normally using net force. So basically what you should have done, the idea behind this question is to use that your net force is equal to mass times acceleration. Your net force is equal to the force applied minus friction minus weight, is mass times acceleration. Your force applied then is equal to mass times acceleration plus friction plus weight. Mass is 60, acceleration we don't know, we had to calculate acceleration. Acceleration would be calculated from, which formula has acceleration, initial velocity, delta x, I don't even know. I don't want to spend too much time on it, I just want to show you that one formula. But anyway, acceleration is calculated with one of the motion equations, which is the 2a is future velocity squared. Is there one that just has initial velocity? Okay, there is one.
You can use the change in x is equal to initial velocity change in time.
Change in x equal to initial velocity
Times the change in time.
Times change in time.
Plus half x. No, wait, that's got acceleration. Never mind. Sorry.
Yes, no, you're right. You're perfect right.
Oh,
Times
yeah.
half because we have everything except acceleration. You're right. Perfect. So you'd use this formula to get a. Thank you. Okay, so again in the same way where we used to try and find v, future velocity, we'll just in this case we'll use that friction plus weight is just mass times gravity. So this is not very difficult. Friction was 12, mass times gravity 60 times 9.8. And so again, all we had to do is calculate acceleration. Can't remember what acceleration was as the answer, but you just get that, put it in here, and you've got force applied. Again, 6 out of the 7 marks you would have already gotten. It's not very complicated, but students really don't understand net force. And net force is exactly the same as net work. It's what forces are working in favor of the motion, what forces are working against the motion. It's income forces plus expense forces. Okay. You good with that? Should we move on to question 2? So this question is typically a question, so I don't want to use this one because this is typically a question where you can't use that formula, because now what we have is we have a guy running into a group of people, okay, which means that he's running at, let's say, a constant velocity. He runs into a group of people, and now all of a sudden there's a collision. That's something different. That is not that's a conversion of one energy into another. Now the energy, so that is momentum. We can look at momentum. In general, I don't think people have a problem with this, but I'll just read the answers maybe. So if I look at the so what happens here, Vladimir is running towards the guards. Vladimir has a mass of 130 kilograms charging towards the stationary guards. Each of them have 50 kilograms in mass in a westerly direction with a velocity of 10 meters per second. So he's running towards them with a velocity of 10 meters per second. Explain using the principles of momentum conservation why immediately after the collision, Vladimir will have a velocity less than 10 meters per second. And can any one of you give me a sufficient explanation why is his velocity less than 10 meters per second after the collision, using the principle of conservation of momentum?
I can't tell you without reading the answer.
You can't tell me without.
Without reading the answer, right?
Is yours correct?
I got 2 marks. I don't know how much it was out of.
It's out of 2, so you were correct. But tell me, well, why did you know then and not know now?
Because I've forgotten.
No, what is the principle of momentum conservation?
It has to do with an isolated system with no additional forces acting on it.
Then what? I didn't hear the first part.
An isolated system.
Yeah.
So there can't be external forces
So
acting on the
there's
system.
no external forces. Then what? You're just describing an isolated system. You're not saying to me what is momentum preservation. Pauline, you've not said a word. What do you...
Oh, sorry.
Let me ask Paulina. Yes? No, you're not answering it now. You might not have been the question. I'm not asking you for the answer. I'm asking for what is the conservation of momentum.
Oh, just a conservation.
No, that's all I'm asking. I'm not asking for the
Oh.
answer yet.
When the initial momentum equals final momentum.
Yeah, it's in momentum before a collision must be equal to the momentum after the collision. Now, what is momentum? It is my mass times my velocity. That's it. So, the system's momentum initially is just the momentum of Vladimir, because the other guys are standing still. So only Vladimir has momentum. The other ones, yes, they have mass, but they have no velocity. So, after the collision, both of them have momentum, because now Vladimir is moving and the guards is moving because he tackled them and he's running with them, which means the mass of the system increased. Does that make sense? So doesn't it make sense? Okay, so before Vladimir is running, he's got momentum, they don't have momentum because they're not running, they're not moving. Momentum, you have to be moving to have momentum. Something that's standing still doesn't have momentum. So before he collides, he has mass and he has velocity. Now after the collision, he's carrying them. But the momentum before must equal the momentum after. So after the collision, mass has increased in a sense. So if mass must increase, velocity must decrease so that the momentum before can equal the momentum after. So let's make it simple. Let's say he's 10 kilograms. Well, he isn't, but let's say he's 10 kilograms and he's running at 2 meters per second. So his momentum is 20. Now he picks up something that's also 10 kilograms. So now he's 20 kilograms, but my momentum must still be 20 kilometers per second, which means the velocity must be 1 meter per second. Does that make sense? Does that explain why his velocity is decreasing? Yes. Because momentum must stay the same. Mass has increased. Not really, but you can think of it like mass increasing if I pick up a stationary object, because he didn't contribute to my velocity. Okay, calculate the velocity that Vladimir and the 3 guards will have after they've been tackled. That is just momentum before is equal to momentum after. Most people got that one correct. If you guys want to, in another lesson we'll look at momentum. Just this formula doesn't apply to momentum, because there's different forces at work. If the three guards were in contact with the wall, guys, this is just something that blows my mind. There's one thing that remains crucial the whole time. You must tell yourself this the whole time. Direction is important. Direction is important. Direction is important. Because look at this, they say the three guards were in contact with the wall for 0.3 seconds. Calculate the magnitude of the force exerted by the wall on the guard. So what happens is, in the previous question, they say that Vladimir runs with the three guards in his arms towards the palace wall 3 meters in front of the wall. Vladimir releases the guards, who crashes into the wall. So I'm running with you, letting go of you, you go into the wall, and now you're bouncing back. That's what they're saying. If the guards maintained the velocity that was calculated, so remember in the previous question, that's wrongly numbered, in question 3.2 we calculated the velocity that they had when they were running with Vladimir. Then he lets go, so it says they are going at that velocity, bumping into the wall. If they maintain the velocity calculated in 3.2 now, as they hit the wall and bounce back with half the velocity, calculate the impulse that they experience. So this is what everyone does. I think the velocity was something, did you calculate the velocity correct? The velocity is 4.64 or something.
It was 4.64.
Okay, so the velocity calculated, the correct velocity that they were going at the wall, towards the wall, was 4.64 meters per second. Now they bump into the wall and they bounce back at half the velocity. So that is the velocity that they have before they hit the wall. Make sense? After they hit the wall, they bump back at half that velocity. So what is their velocity that they bounce back at? You can use your calculator. I'm not opposed to that. They hit the wall at 4.64. They bounce back at half the velocity. What is the velocity that they bounce back at?
2.32.
No.
I'm saying it's not.
No, it's not 2.32. It's negative 2.32.
Oh, yes.
That's the problem. If you say the future velocity is 2.32, you are saying they just slowed down a little bit. They didn't slow down a little bit. They went to 0 and back. So the difference in velocity, future velocity minus initial velocity, if you just take 2.32 minus 4.64, that's now the difference in velocity, you get 2.32, negative 2.32. But it's not, it's negative 2.32. The change in velocity is negative 6.96. Do you see the change in, this is the change in velocity. So if you didn't put the negative, then your change in velocity would have been negative 2.3. That just means they slowed down with 2.32. Okay. If they slowed down with negative 6.92, but they were only going at 4.64, it means they went to 0 and back. Does that make sense? Now that makes a difference in the impulse, because impulse is just change in momentum, which is mass times the change in velocity. And now you can see what a big difference that answer will make. And so guys, please keep it in mind. When something bounces off, your change in velocity actually goes from future minus initial. If it changes back, it's actually future plus, because it's a minus minus. Does that make sense? My future velocity, if I take coming back as positive, then my future velocity is positive, but my going velocity should be negative. So it's negative initial velocity, which becomes future. Okay, I might just be talking into the air. You might not understand what I'm saying. All I'm saying is, if you just keep your signs correct, you cannot make a mistake here. But if you don't put that as a negative, then it is, then you're actually just looking at it slowing down a little bit. But it's more than just slowing down. It's slowing down to 0 and coming back. Okay, so that's an important part. And then the next one is just what is the work that the wall does on it, and that is just momentum over delta t. Okay, change in momentum over delta t. So it's a simple substitution question. Okay, so the answer you had here, you just substitute that 0.3 in, and then you get the net work done by the wall. Okay, let's quickly go down to the next question. When Vladimir jumps vertically upwards. Okay, so let's read the question. During a dramatic escape from prison, Flynn Rider is projected. Have you guys watched this movie, by the way? This is Tangled. It's brilliant. I didn't set this paper, a friend of mine did. But the movie is called Tangled. It's very, very cool movie. Anyway, during a dramatic escape from prison, Flynn Rider is projected vertically upwards into the air. Okay, when Vladimir, of mass 130 kilograms, jumps from a position of 3 meters, so there he's standing on the wall, he jumps up 3 meters above the ground onto a stationary cart. So here's a cart, he jumps up, lands on the cart, and then projects Flynn Rider into the air. Flynn has a mass of 60 kilograms and the prison wall is 8 meters high. What effect? The effects of air friction can be ignored. So what you need to know is that there's 2 parts to this. There is the part where he jumps up in the air, and during that time acceleration is constant. The moment he lands on the cart, there's a collision. There's a change of energies going from kinetic energy is translated into Flynn Rider's kinetic energy. You see, so this is 2 systems, as I've been talking about. So we can use our formula, okay, because there's something that happens before the collision and there's something that happens after the collision. Does that make sense? In the previous question, it was all about the collision. What happens when he runs into these guys? It didn't ask anything what happened before or after the collision in terms of what happens there. It was all about the collision. I hope that makes sense. Okay, so let's quickly say, when Vladimir jumps vertically up, he leaves the platform with an initial velocity of 4 meters per second. Calculate the magnitude of the velocity wherewith Vladimir will land on the cart. So, let me copy this. Okay, so when Vladimir jumps vertically upwards, he leaves. Okay, so this is a very simple, most people got this question correct. It's a very simple vertical projection question. I just want to show you can also do that with your formula. Okay, so this guy is jumping vertically upwards. During this upward jump, okay, so he's jumped upwards, is there any applied force during the upward jump? Not when he's lifting off, during the upward jump, while he's moving. Is there any work that's being applied? So what is the income energies and what is the expensive energies?
Expenses. Weight.
Weight? Is weight?
This is jumping, so I think it's really
but it is going downwards. So is weight an income or an expense?
Oh, it's an income. It's an income.
Well, it doesn't matter really how you choose it, as long as you interpret your final sign as, because we're thinking, whereas there's no work applied. Work applied can only be when you're falling. The only work that's being applied to you is gravity. So in this case, the work done by gravity must equal the change in kinetic energy. That's it. Now, if gravity is in your favor, in the end you'll just have to translate the information. Or the sign, you'll have to interpret the sign. So work done by gravity, that's the only thing that's applying here. So it's going to be an income or expense. So work done by gravity is mass times gravity times the change in height is equal to half mass times future velocity squared minus initial velocity squared. Now, you can just see on both sides of this equation, we've got mass. So, I don't need to use mass. It will just divide away anyway. You see that? I can also see, well, okay, let's do that. So gravity is 9.8. Height, what is his change in his height? So remember, he's jumping up and he's falling down, he's reaching the bottom. But what is the change in his height?
3 meters.
3 meters. It doesn't matter how high he jumped. He's jumped from 3 meters high. Does that make sense? So his change in height, he used to be here, but now he's there. It doesn't matter the in-between path he took. So change in height was 3 meters. The question asks me, what is the velocity he lands with on the cart? So what am I trying to calculate?
Final velocity.
Final velocity. What is his initial velocity?
0.
When Vladimir jumps vertically upwards, he leaves the platform with an initial velocity of 4 meters per second. So 4 squared. There I go. There I've got a formula, multiply both sides, so that's 9.8. Now the problem with teaching this formula is I can't teach this formula from the beginning of the course because we've not done work yet. So it only makes sense once we've actually done energy. So I get future velocity squared is 58,8 plus 16. So future velocity is the square root of that. But now here comes an important point. Plus 16. Now I take the square root of this answer. Oh, took that. 74.8 square root of that. 8.65. 8,65 meters per second. But I took the square root. Which means it must be plus or minus. I multiplied my half to this. So when I multiplied this with 3, I multiplied with a 2 as well to get rid of the half. So here it doesn't really matter. Let me quickly show you why. If I jump upwards with 4 meters per second, it's the same as jumping down 4 meters per second as well. Because if I go up with 4 meters per second, the moment I reach here, I'm going down with 4 meters per second as well. That is why it doesn't matter how high I go. The information jumping upwards or downwards with the same velocity will reach the same final velocity. If I throw something up in the air with 10 meters per second, it will land, the velocity it will have when it reaches the ground is the same velocity it will have if I threw it down at 10 meters per second. Seems a bit weird, doesn't it? But it's because when it goes up, by the time it comes back to me, it has the velocity that it had when I threw it up. And that is why it isn't important to calculate how high it went. And that is why direction in this case doesn't really matter, because I am squaring my velocity anyway. A negative will anyway become a positive. Positive will anyway become a negative. So, but in the end, I must just remember, if I chose upwards, just remember to give your answer as downwards. Okay, it doesn't matter what you chose, up or down, it's plus or minus anyway. But remember to put downwards as your. State the principle of conservation of mechanical energy in words. In the absence of, or in the presence of conservative forces, mechanical energy will be preserved. Mechanical energy is the sum of kinetic and potential energy. Okay, won't go into that. Assuming that the collision between Flynn and Vladimir is elastic, prove using energy principles that Flynn would be projected into the air at that velocity. Now here again, can we use our formula?
Energy principles are. I think yes.
No, because we're talking about the collision.
Oh, energy principles.
So we're talking about the collision. So if we're talking about the collision, we either use principle of momentum conservation, or in this case, they specifically say that it is elastic. Now we need to know what elastic means. What does elastic mean? Elastic collision.
Initial kinetic energy is equal to final kinetic
The
energy.
total so you're right. Total, I'm going to use K and a different color. Total initial kinetic energy is equal to the total final kinetic energy, which means we should consider the initial kinetic energy. So what's happening is the guy's jumping on a cart. Here's a cart, there's a guy standing. Whoa, weird looking guy. There's a guy standing on the cart. There's a guy jumping on the cart. Okay. Now, the moment he reaches the cart, there's a collision. Do you understand? So we're not considering this option. We're considering what's happening here. So we need to know how much kinetic energy does he have when he reaches the cart, plus the kinetic energy that the other guy has. Now that guy is standing still, he doesn't have any kinetic energy. So initial kinetic energy is a half mass times velocity squared, and we only have Vladimir. Only Vladimir has initial kinetic energy. And then afterwards, Vladimir is stationary. He jumps on the cart, so he's standing still now. So afterwards, we only have Flynn's kinetic energy. So half mass times velocity squared for Flynn. No, it's not future velocity, it's Flynn's velocity. So in the previous question, we calculated what Vladimir's final velocity will be when he reaches the cart. So here we get a mark for that. We get a mark for knowing that kinetic energy is half mass times velocity squared. Now I simply multiply in. This is Vladimir's kinetic energy is a half. Vladimir was, how much was he? 130. Yes, 130 kilograms. He was traveling at 8,65 squared. So again, you can see because we're squaring the direction, the sign is not very important. Is equal to a half mass times, and Flynn is 60 kilograms. So Flynn's velocity is what we're trying to calculate. And there it is, 5 marks. That's ridiculous. So we've got 130 divided by 2 times 8.65 squared times 2 divided by 60. Okay, that is the future velocity squared, 162.12 meters per second. And then future velocity is the square root of that, 12.73. Okay, so notice guys, your theory is very important. If you don't know what elastic collision is, you can't answer this question. Okay. If you know and understand what principle of conservation of momentum is, you can answer questions like that other one, why does his velocity decrease when his mass gains, when he gains mass? Okay, there's another question that now relies on this. By means of calculation, determine if Flynn will be projected high enough to land on the top of the wall. Okay, so in the previous one, it tells us what velocity Flynn starts with. Now they ask us, if he starts with this velocity, will he be projected high enough to land on an 8-meter wall, I think? The prison wall is 8 meters high. Okay, can we use our formula now? Is it about a collision?
No.
No, it's now about his traveling through space. It's only in the air. So we can use our formula. Again, you don't have to. I just want to show you you can. What is, he's traveling into the air, what is his energy, income and expenses? Is there any income energies while he's traveling into the air? Any force in his favor? No. Okay. Forces against him? Gravity. Again, while I'm traveling in the air, I can always, if it's just a free fall, traveling in the air, no forces acting on me, I can always just use this formula. The work done by gravity is equal to half the change. Work done by gravity is mass times gravity times change in height, not just height, but change in height, and that's what we're trying to calculate. Is the height that he's going up into the air 8 meters or more? Does that make sense?
Okay, so I just wanted to ask you, why don't we put a negative? We don't put a negative.
You could put a negative. Yeah, you can put a negative because it's an expense. You could. Okay, so on this side we have half mass and then future velocity squared minus initial velocity squared. Let's see if we've got everything. Again, mass is not important. Okay, mass on both sides will cancel out. That is why when you throw an object into the air, its mass, it doesn't matter what mass it has. Okay, it will fall at the same velocity as anything else as long as we ignore friction. Okay, so gravity is 9.8. We want to work out what is his change in height going to be. We have mass, half. What is his future velocity? And his initial velocity?
Future is 8.65.
His future velocity.
Yes.
So now think about it. He's traveling in the air. You're saying...
Oh, well, I was looking at the wrong...
Okay.
I don't know. What's the future velocity? Wouldn't it be 0 because he lands?
Yes. Not because he lands.
Well, because he gets to his maximum height.
We're actually asking what is his maximum height. That's actually what we're asking. Does that make sense why we're asking that? If I throw something up in the air and I ask if it's going to be able to go over a wall, aren't I asking what is the maximum height it will reach?
Because it stops when it reaches.
Because at some point it stops, meaning its future velocity is 0. So future velocities, we want to know how high is it when it reaches, when its velocity is 0, because then it's starting to fall down. So that's actually the question. So we want to know when velocity is 0. What is my initial velocity?
Is it not 12?
That's the 12.73. So they were very kind to give you that answer in the previous question. And now if you work it out, I think it's 8.27. When I used to teach at school, I had 3 classes, 3 metric classes, and I would do financial maths on the board, and then I would remember what the answer was from the previous lesson. Then I'd stand there and then I write the answer. Yes, and I thought, wow, so you can do it without a calculator. Yes. Sorry, I'm doing it the wrong way around.
So if we didn't calculate the first one, so we would have to find out.
That's why they give you the answer. If they ask you to show that something is this, it's probably because they want you to use this answer in the next question. And if you got the wrong answer, we have to follow up marking, which makes marking very difficult. If every student you have to recalculate that they do it correct. So usually what we do is we ask you to show that it's less point, you get less points for a question like that because you already have the answer to work towards. But in the next question you can use the correct answer. And then and work from there. So 1.6 divided by 2 is equal to divided by...
I know to choose the direction in this question.
Yes, of course. Yeah. I don't think it would make much of a difference, but because very few of these questions actually had where direction was important. But change in height is 8.27 meters. Okay, here it wasn't so much the question wasn't how high he goes, so direction isn't important. The question was, does he reach the wall? So if you didn't say yes, you don't get the answer. You don't get full marks. So the wall is only 8 meters, but he'll go 8.27. So he's going to make it just to the top of that wall. Okay. Here's the questions that we usually use these formulas for. Okay, Ralph is searching for his lost medal inside an arcade game. This whole question paper was based on cartoons. This one is, what was this? Wreck-It Ralph or something. For his lost medal inside an arcade game called Sugar Rush, he helps Vanellope to learn how to drive a go-kart. With Vanellope seated inside a go-kart, Ralph pushes Vanellope and the go-kart up an incline that makes an angle of 23 degrees with the horizontal. The surface of the slope has a kinetic frictional coefficient of 0.5, okay, and the length of the incline is 60 meters. The combined mass of Vanellope and the go-kart is 123 kilograms. The diagram shows Ralph as he pushes her up the incline. Draw a label force diagram showing all the forces acting on the go-kart as it's being pushed up the incline. Okay, this, strangely enough, people get wrong. They get 3 out of the 4 forces right. 4 marks, lovely 4 marks. Okay, and strangely enough, it seems like they don't understand what... So there's my surface. You shouldn't really draw in the surface. So let me draw it in with maybe a grayish color. Okay, so there's my surface. And then just rub it out afterwards because it might be mistaken for forces. Okay, and now to draw in all the forces. What forces are acting in on Vanellope? Normal force, which and what do we know about a normal force?
Perpendicular to the surface.
Perpendicular to the surface. So when you draw in your normal force, it has to be perpendicular to your surface. So there's my surface. It must make a 90-degree angle. Okay, what else?
Weight.
Sorry?
Weight.
Weight? What do we know about weight? It's always down, straight down. And now it seems a lot of people put the normal force and weight in the same direction. So they either put the normal force there or they put weight there. That's a common error. No, normal force is perpendicular to the surface, weight is directly down. The only time that they're in line is when an object's going up or just standing on a straight surface. That's the only time they're in line. Okay. Other forces?
Force applied.
Force applied, is it up or down the incline?
Up the incline.
Up the incline is a force applied. And then what other force?
Friction.
Friction, up or down the incline? Is it always down the incline? Opposite direction, and she's going upwards. So that's why it's down the incline. So there is, and let's label it. They did tell us to draw and label. So if there wasn't labels, okay, so we can just label normal force with an N, weight with W, force applied as FA, and frictional force with a lowercase f. That would be sufficient. Okay. Calculate the frictional force experienced by the go-kart as it's being pushed up. Now we could use our formula, but in our formula we have too many unknowns so far. There's a quicker way by just using the direct formula for frictional. Is it static or kinetic friction?
Kinetic.
Kinetic? What is the difference? Do you know? What does static mean? It's stationary, yeah. So in other words, the reason why even though this is at an incline, why this pen is not sliding down is because this surface has static friction. It has friction that will hold the pen in place until the normal force, like if I lift it up, the more I lift it up, the less normal force gets. Okay, until the normal force is too small to keep it up, to overcome gravity. And then it starts sliding. And then the moment it starts sliding, it still has friction, but then it's kinetic friction. Kinetic friction and static friction is not necessarily the same value. Okay. So, kinetic friction's formula is the kinetic friction coefficient times the normal force. And we saw earlier that the normal force is weight times cos of theta. And weight is mass times gravity. So, kinetic... Now, this formula is not given on your formula sheets, so know it, please. Mass times gravity times cos of theta. So 0.5 mass is Penelope's mass, 23 kilogram. Gravity is 9.8. And cos of theta, where theta is the angle of the incline, is 23.
I think I made a mistake here. I said 180. And
oh, is it?
yes. I don't even know why.
Okay, 5547955.
Oh, now I think I do. So if, let's say if the surface was straight like this,
yeah.
So it was going to be 180.
No.
Or 0.
It's 0 because it's the angle that I make with the horizontal. So if I am so horizontal, what's my angle I'm making with the horizontal?
0.
0.
And then
when it's vertically upwards,
90.
What is the angle that I make? 90. What is cos of 90?
Cos of 90 is adjacent over.
Sorry?
I'm saying cos of 90 is adjacent over hypotenuse, which is
cos of 0 is 1. Cos of 90 is 0. So what if cos of 90 is 0? What is the frictional coefficient for an object that is standing on a surface that's 90 degrees? 0. That makes sense? What friction is keeping this in the air? Nothing. Do you understand why there's no friction? Okay, there's no surface. Okay. Because there's no normal force. Okay, calculate that we did. State the work energy theorem in words. Okay, net work done is equal to the change in kinetic energy. That is our powerful, powerful formula that can really calculate almost any mechanics question. Okay, the go-kart is being pushed up the incline with a constant velocity. If I know constant velocity, what do I know?
Initial and future are the same.
Initial and future are the same. Or, what else do you know?
No acceleration.
No acceleration. No net force. If something is going at a constant velocity, the net force is 0. If the net force is 0, then net energy is 0, because net energy is net force times delta x. Okay, so in other words, we know that the net energy must equal 0. Why? Because my change in kinetic energy is not changing. As she's being pushed up this incline, her kinetic energy is constant because her velocity is constant. Does that make sense? Okay, I tell you what. Let's say we didn't know that. Let's say you, for some reason, you don't understand that the change in kinetic energy is 0. My kinetic energy is not changing because my velocity is not changing. Okay, let's say you don't get that. That's fine. Let's look at, they ask us to calculate the work done by Ralph. Okay, so can we use our formula? Yes, there's no collision involved here, so we can use our formula. Let's say, what's all the incomes? What energy is an income energy?
Force applied.
Not force applied, work applied. Work applied, that's actually what we want to calculate. Okay, so we want to calculate work applied. Okay, do we have any other, so she's going in this direction. Is there any other forces or energies that adds energy into, that's in our favor? Nothing. Okay, you guys get why there's nothing? The normal force, by the way, cannot do work, because your work, the normal force is always perpendicular to motion, which means it's always cos of 90. It's always 0 work. When I do, if I lift something straight up, I can't do any work horizontally. I have to move it horizontal to do work horizontal. Okay, so, but anyway, that's not. Normal force don't do work. A surface cannot add energy into a system. It's as simple as that. Surface doesn't do anything but counter gravity. Okay. So the normal force doesn't do anything, and you can see the other two forces are kind of in the opposite direction, as not directly opposite, but countering. So the two expenses is my work done by friction and my work done by gravity. And that must equal my change in kinetic energy, which is a half mass and future velocity squared minus initial velocity squared. Now you can save yourself a lot of trouble by just knowing that if I'm going in a constant velocity, my change in kinetic energy is 0. But let's say you didn't know that. What you, Masande, at least know is that your future velocity is equal to initial velocity. So, if these two values are equal, what will I get when I subtract them? I'll get 0. And so this whole side, this side becomes 0. You get that? Okay. So here we got work done by acceleration. I'm not going to change this into force applied times delta x, because I want work applied. So I just want this value minus frictional, work done by friction would be frictional force times delta x. Work done by gravity is mass times gravity times delta h, the height, change in height. And on the other side, it simplifies to 0. Now here we might have a little bit of a problem, because...
So,
yes.
Why aren't we changing the... Are they specifically saying we want the work of...
Yeah. What is the work done by Ralph? That's what we have to calculate.
And previously, when we're substituting the displacement, what would they say?
When did we use this for?
Yeah,
This way.
Yeah,
we always use this,
yeah.
unless they tell me that they want work applied. Then I don't. Work applied is the force applied times delta x. Okay, so you could have replaced it, gotten force applied, and then substituted back into this formula. So you could always use that, but then you again have to go substitute back into work applied.
But previously we were substituting the height, but this time we didn't, because we're not given it.
What do you mean we were substituting the height?
Work applied equals to FA, then delta x, Then we
Yes.
substituted delta x with we're given a height.
Yeah.
But this time
So,
we didn't.
and
We're
are
just
you
keeping it-
talking about this value here?
Yeah.
Why aren't I writing it as force applied times delta x?
Yeah.
Because what I'm trying to say is that in the question, they're asking for this value. So if I do this, you can do that.
Okay.
But in the end, you anyway going to take the answer that you get for force applied and multiplying it with delta x. So why not just keep it as work applied in the beginning? Does that make sense? Okay.
Sorry, I think we should also use like a different blue one because it's hard to see.
Oh, sorry, I don't look there.
It is.
Okay, I'll stick to green. Is that okay? Can you see there now?
Yes.
For now, okay, thank you. Warn me. Okay, so now we're going to substitute. Work applied is what I'm trying to calculate, minus my frictional force is what I calculated in the previous question. If you got it wrong, then we do follow up. Okay, delta x is the displacement, they said is 60 meters, minus mass times, mass is her mass, okay. Her in the go-kart is 123. Gravity is 9.8. And now, what would we use for change in height? The 60? Did her height change with 60 meters? No. Her height changes with this value. Okay. If you say 60 meters, you are saying that gravity is the only time height is equal to displacement is when it's in upwards and downwards. Okay. So here we're going to have to calculate delta H. In other words, we're going to have to find out what is the change in her height. And then that's equal to, so there's two unknowns here. We just want that unknown. But again, up to this point, you almost get all three your marks. You get at least 2 marks. So you get at least half the marks here for this and for that. Now you'll get another mark for calculating the height. Now how will we calculate the height here?
Can we use those cos tree?
Oh, it's a triangle.
Yeah, it's a triangle.
Here's my triangle. Jessica, all these guys are doing, I don't know how many of them are doing trick already.
Don't miss it.
You don't miss it. Okay, well you need it. Oh wait, I shouldn't use. Okay. Notice this is my opposite. It's the opposite the angle I have that I'm trying to calculate. It's the hypotenuse that I have. So what am I going to use to calculate H? I use what I call sine, the ratio triangles. I'm going to use sine, thank you for that. I'm going to use sine. Sine is opposite over hypotenuse. Okay, so this is not height, that's hypotenuse. So if I want the opposite side, this side, I must take, I close my hand, I put my hand here, I want this side, so I must take my hypotenuse times sine of my angle. So delta H is my hypotenuse, which in this case is 60 meters times sine of 23. So the change in height is 23 sine times 60, 23.44. And so work applied is equal to, and now I'm just going to add those two things. So it's 123 times 9.8 times this this answer here, 60 times 23 sine. Okay, that is this part. This is the work done to overcome gravity, plus the work to overcome friction is 554.7 times 60 is equal to 61,500. Joules. I think so. Doesn't look familiar. I might have it wrong somewhere.
I've got 28,814.
Okay, let's take your answer. It doesn't sound familiar either. I might have just made a mistake now with the calculator. So 554.79 times 60 plus 123 times 9.8
60.
times 60 times 23 sine. Oh, I get that same answer again. Do you get the same answer again?
No, I don't know what I've done wrong.
Oh. I suppose it's this answer. Doesn't look familiar, but then again, very few people got this. So I didn't see the answer very often, if ever. Okay. Okay, and this is a Doppler question, so I'm going to stop here. So, what do you guys think of that formula?
Oh, it's amazing.
It is helpful, as long the only place I can't use it is in my collisions, and in collisions it's either momentum preservation, which means total momentum for total momentum after, or elastic collisions, which means energy before is equal to energy after.
I just wanted to understand the zero part. I'm still confused. We used zero because whatever his name, Ralph, started from zero and he pushed to at the end. He pushed
What
to
did
zero.
what did we say is equal? What is zero?
You said 90 zero, something like that.
No, no, we use zero. So this value, are we talking about this value here? Why did we use change in kinetic energy is equal to zero?
Yes, that's what I'm saying. That's what
So
I'm
you're
asking.
asking,
Yes.
why is the change in kinetic energy zero? If something is zero, so in other words, if the change in kinetic energy is zero, it means that the kinetic energy, the future kinetic energy minus initial kinetic energy, that is change in kinetic energy. Do you get that? If this is equal to zero, it means the kinetic energy, my future kinetic energy, is equal to my initial kinetic energy. Okay? Now, so let's put in the values. That means a half mass future velocity squared is equal to a half mass initial velocity squared. Now, you see in this equation, there's a mass on both sides, so let's eliminate the mass. There's a half on both sides, so let's eliminate the half. So in other words, what we're saying is that the future velocity squared is equal to the initial velocity squared. That's only possible if future velocity is equal to plus minus initial velocity. Okay, so just ignore the plus minus for now. It's additional explanation there. When is my future velocity equal to my initial velocity?
When it's at the top. When Ralph is
No.
when-
I'm not talking about this story.
Oh, the story.
What does it mean if my future velocity and my initial velocity is equal? What does it tell you about my motion? It's constant. So if I'm traveling at a constant velocity, my future velocity will equal my initial velocity, which means my change in kinetic energy is 0. Remember, kinetic energy is how much energy I have because I'm moving. If I'm not moving faster, my energy is not changing. My change in kinetic energy remains the same. You don't seem convinced yet. It's a great question. I wish people will battle with this more, because then they won't forget it. It's one of those things that 80% of the people just don't get. Constant velocity. Remember Newton's laws. There's the 3 laws. The first 2 laws. The first one says that if an object is in motion or is stationary at a constant velocity, it will remain as such unless an external force acts on it. Okay? Which means, if I'm going at a constant velocity, unless an external net force acts on it, if I go at a constant velocity, it means there's no net force acting on me. It doesn't mean there's no force acting on me. It means there's no net force. The income forces and the expense forces cancel one another out. There's no net force. Make sense? Okay. So if there's no net force, remember, net force is mass times acceleration. So that's the second law. Acceleration is directly proportionate to the net force and inversely proportionate to the mass. So if I'm going at a constant velocity, there's no net force, which means net force is 0 over mass, so acceleration is 0. Okay. I can't think of more ways to say it, but as long as you know that when velocity is constant, my kinetic energy is constant.
So they mention it in the question that it's constant, or
sorry?
I'm saying they mention it.
Yes,
say,
yes.
Constant.
Okay, maybe that's the problem. Is you didn't see that.
Yes.
That might be the problem. That is why we use 0. They said the cart is being pushed up the incline with a constant velocity. The moment they say constant velocity, there's no change in kinetic energy. Sorry, trying to explain something that you would have actually got if you just knew the question. Okay, cool. Any other questions on this?